And it gets even more puzzling when you begin to look at the detailed results. So the detailed results are really cool. So they go something like this. If you make a plot then, because what we want to do is we want to see, okay, there are these peaks. Where are they and how is that affected by this voltage? Because this voltage, remember, at the end of the day, I can use to control how quickly my electrons are coming down. So if you display the results in the following very clever way, you get a result that really makes your hair stand on end. So I want you guys to see this. So what we're going to plot on this axis is I'm going to plot the angle where the peak happens. And we're going to see actually there can sometimes be multiple peaks. But it turns out the best way to plot it is not as the angle where I see the peaks, right, but the sine of the angle where I see the peaks. So of course the maximum value that the sine can have is 1. At sine of 90 when I'm scattering all the way down here at 90 degrees, right? And on this axis, the clever way to plot this is to plot 1 over the square root of E times the voltage V. And we like that combination because voltage, remember, is an electric potential times charge gives you actual potential energy. So this is a direct measure then of the kinetic energy of my electrons as they come down and whack that nickel target. And that turns out to be the right way to plot it for some reason, 1 over the square root. So for example then, if I take this data point that I'm talking about, right, the sine of 50 degrees is somewhere around 0.8 or so. And then you come to a point, say here, right, where then this x-axis corresponds to 1 over the square root of E times, as we said, 54 volts. And that would then correspond to the experiment that you see up here. Now what's interesting is if I increase this voltage, right, that would tend to move me more towards 0 along this axis. And as I do that, the angle actually does decrease, but in a really cool way. So what I get is a perfect linear straight line like so. And I can continue this line to lower voltages to where then that maximum goes to 90 degrees. And then, of course, at that point, it completely disappears. There's no more maximum at all because I can't access any larger angles. Okay, so that's interesting, and that curve then we could characterize as some kind of a slope, which I will call alpha, times x, because this line actually runs directly through the origin. So its equation is slope alpha times the horizontal variable, but that horizontal variable I'm calling 1 over the square root of E times V. So this curve is just alpha over the square root of E times V. Okay, fine. Now here's the freaky thing. I actually don't get just one straight line. I get another straight line. When I get down to a low enough voltage, somewhere around here, a higher voltage, somewhere around here, a second maximum will begin to appear, and that one actually will come in straight to the origin. And that also has a particular functional form associated with it, but the freaky thing is this thing has a slope that is exactly twice the previous slope. An integer times it. And there's more. There's another curve that will come in at even higher voltages that will have 3 times the slope. So this will be 3 alpha over the square root of EV. So it's really kind of an uncanny, hair-raising type of a result. When you see something like this, you know there must be something going on underneath of it. And it certainly has nothing to do with, funky tent shapes or something like that going on. There must be something more fundamental that can produce these curves that are all occurring at exact integers of each other and all being perfect straight lines.